Welcome everyone to our first talk of today. In the session Human-Robot Interaction, we have Dr. Roche with us. He's the CEO of Clover.AI, and he's going to talk about human-robot interaction with natural language logic a step closer. Please, Dr. Roche, the floor is yours.
Thank you very much, Renzo. So I changed the title a little bit. I'm just going to be a bit more generic about the place of natural language in human-robot interaction, in particular in one particular question, how to build an intermediate representation. And before I jump into that question, I'd like to make a small detour and really ask a non-engineering question. So why are we doing that? I mean, if I'm just an engineer, I'm just doing that because I can. But I mean, there are also engineering questions are linked to scientific questions. And here, the interesting question for me is trying to use robots as a mean to really understand who we are as humans and in some way before robots understand us. And I'm just going to give one small example about different meaning of understand, because we are at a time when there's a lot of confusion. So let me give you an example of one robot that I think would be dangerous. It's built with today's technology, and it's practically, you can say it exists. And it probably understands us in some way. So let me take something. Imagine something like Twitter, very close to Twitter. So what is Twitter? It has, if you think of it as a living organism, right? It has a sensory system in the sense that it perceives some things about the world, right? It can see what people write and then some other things, what people respond to, and then how they respond to it, what they promote, what they block. So this is the perception of the world. Then they have a model of the word. It means that they are trying to figure out, to predict a little bit how users are behaving. And then it can do things, and the things it can do is, it looks very small, right? It can basically do two things. It can promote content, and it can destroy content. Right? It can destroy content. That's the big question that we have these days about censure, right? You block, you don't like this content, you block it, you think it's dangerous, you block it, or for any other reason you can block it. So you have this organism can act on the world. It doesn't look like much, but of course it's 100,000 times per second, so it's quite substantial. And it has a purpose, which is something like optimize the number of interaction, or you can also see it as optimize revenues, right? So it's an organism that tries to maximize its resources. And now let's go back a little bit to what it means. What is the model of the world it has? Assume it's not exactly Twitter, but something like that. It assumes that people act according to certain parameters, their interests, but also maybe emotions, anger, fear, this kind of thing. And then it has something, a huge deep learning model. So let's say GPT-3, 170 billion parameters. So what can you do with that? Every message which is being written can go through that. And for instance, you can do sentiment analysis, but not the traditional sentiment analysis. You can also detect things like anger and fear. And you can imagine the system is trying to maximize revenues, traffic. It might start to promote things that are driven by anger, because just it observes that it increases traffic. So the scary thing there, I mean, people say, of course, I'm referring like science fiction, Skynet, destroy the world. It doesn't have, you don't give an AI system the key to the atomic bomb. But here, the action it can do is very small, right? Only promote content and destroy content. But it can do that very fast, very consistently at a huge scale. And in a way, we don't understand it. We give it, we have a huge GPT-3 model, we have samples, but we don't know samples of what. And the result is increasing anger, because that's just what it does. It's increase its traffic. So you have a purpose which looks neutral on the surface, increasing revenues, increasing resources, but actually it's a very destructive goal. And it's potentially dangerous at its scale. So it's kind of interesting, as you say, this in some ways, this system understands us better than we do. It will detect that we are angry before we are angry, right? It will detect that maybe we are promoting a point of view without ourselves being aware that we are promoting this point of view. So in that sense, we have this understanding of us, but it has it's like a lobster or a crab. It understands us based on its purpose. And I think we are reaching a point with this neural system in which basically, because we don't understand what's happening, it's becoming dangerous because of the scale at which it's being used. And there might be a point pretty soon in which people will say it's just not possible to use these models anymore. So now this is some kind of understanding, but I want to talk about a deeper understanding. And my original question was the following: how do you interact? So you go back to robots, you have natural language input, you have actions that the robot can do, and sometimes you have feedback. And the current model is usually you have some kind of mapping about what the user says to some function call, which then directs action. And then sometimes it's a bit more complex than that. You can have a feedback loop, you can have a state model such that the mapping depends also on the state. But that in general, that's what's happening. And what I'm interested in here is this intermediate representation K. Can we do differently? Can we actually map natural language input to something that represents some kind of K, so knowledge, and then that can be mapped into not simply a function call, but possibly a program, and a program that can be generated. So that's the question I'm going to explore here. I'm going to say that we can do better than just use neural networks in which we don't understand anything. So this K, finding K is very complex, and it has already been solved in some ways. So that's the good news. The bad news is that it took us 100,000 years to solve it. And when you think about it, right, it's exactly what language is. What is language? Evolution, you can think of it. We had way to think without a language, right? Chimpanzees think, they think differently, but they think. And then we don't really know, but let's say 100,000 years, it took us, we were mapping whatever thinking model we had in our mind into something called language. And what's language? You can see it as something as simple as it's, imagine that you are in the dark, like you live in the dark 50% of your time. You communicate like chimpanzees through gestures. You are in the dark, gestures don't make sense. And then you switch to something a little bit like bats, right? You recognize gestures in the dark. What are the gestures you can recognize in the dark? That's actually the gesture that your mouth and your tongue do, and the sequence of those, right? So the sounds that you hear are actually gestures. That's why there is a continuity between the language of hands and the language of the actual language. But what does it do while doing that? First, it's one-dimensional, right? You say it deploys in time, it's a sequence of move, and then it's discrete, right? It's a discrete one-dimensional sequence. So when you think about that, thinking without words is a huge part of what we do, and it's big. We don't know really how big it is, but it's big. And we have mapped that into that one-dimensional sequence. That's a major achievement. And what we are trying to do in some ways is reverse this mapping, try to find, can we move that mapping backward? So a lot of people have tried that. And the first, I would say the first attempts to do that is just writing, right? If you think about what is writing and how it started, so it's very interesting. Writing appeared more or less 3 times in the history of mankind, right? In Mesopotamia, cuneiform probably, and then in China, completely independently, and then in Mayan language in the American continent. Exactly 3 times. And all 3 times, it appear the same way, more or less. The same way in what sense? It starts by shapes, right? You try, so it's an abstraction. This is not sounds, these are shapes. So you have top left here, on the left, you have cuneiform, the older form on the top, the newer one on the bottom. You have Chinese in the middle, and then you have the Mayan language. And basically, you have drawing, you have some technology input there on cuneiform. It's on you have tablets in which you can write, you can simplify the drawing. And in Chinese, you simplify the drawings through brush. It's interesting because it's the same process of going from a continuous drawing into something which is discontinuous, a sequence of strokes. But in some ways, it's the same idea. Not sounds, but drawing. And then if you look, so I'm going to look at Chinese a little bit because it's very interesting, because it's very interesting to see why writing failed in its original attempt, because we're going to fail. I mean, we are failing still the same ways. So give one example here. You can do very elaborate things. You have a drawing of a head. In Chinese, you have a drawing of a foot you put together. It's a pathway, right? It's the word Tao, like the path, the way. Here is another. So you can even do things. How do you represent something as abstract as not, right? Not is extremely abstract. In some ways, you can say it's not even part of, or very indirectly part of mathematics. So here it's two. I mean, you can. There are different analyses, but one is just people back to back. That's the meaning of not. So you can do fancy things. You can do things like how do you express the act of explaining, right? It's to separate, and here separate. It's you have three drawings put together. You have a knife, you have an ox, and you have a horn. If you cut, it's the act of cutting the horn of the ox. That's what separate or explain means. So you can have very elaborate things. And you have something which is like here is the word meaning. So for it's just for name or word or what's spoken. And what is it? It's the word which this is the moon, and this is a picture of the mouth. And this is basically the sound which is spoken by the mouth in the dark. And if you think about what I just said about language, about the appearance of language in the dark, the gestures in the dark, that's exactly what this word says. It's a pretty incredible word. It's a very, very brilliant definition of language itself. It's what's being spoken in the dark, and it's actually the name of a person, so it's the way to call somebody. So that you see the limit of a system. You have a character for listening. It's beautiful, but it takes 22 strokes to do it, and then you can simplify it, but there is a limit to that. And the way writing has solved this problem is basically the same. This is the word for ant, E, and it has two left part, which is an insect, some kind of insect, and the right part is just the word for justice, but it has nothing to do with justice, just the fact that justice is pronounced E. It's like it's the same pronunciation. So you borrow pronunciation from another word and use that to build your new word. So basically what you have done here is give up with your original goal. You had the goal of describing what you think with drawings, with something which is not language, and then you realize it hits a wall, and then basically what you do is go back to language itself. And if you look at analysis of Chinese characters, about like 80% are like that, and only 20%, which is already substantial, is based on drawing. So this is interesting because a lesson for that is that sometime to draw K, you may have to leave some pieces of a language in it. So I'm going to go through other kind of attempts which are interesting to understand it. Because defining K is so complex that you need to, there are multiple angles, and each attempt sheds some light on what we are trying to do. So if you think about like set theory, for instance, so invented, you can say by Cantor, and then you have like one good the most used theory is the Zermelo-Frankel set theory. And a large number of these mathematical concepts actually are derived from language, right? They exist in language first, and then mathematicians have tried to formalize it. I mean, it's true in Euclid already. I mean, it's true all in the history. If you look at logic, this is really the starting point of the thinking is pretty much systematically language itself, and then say, okay, can we express it into something completely formal and set? So Zermelo-Frankel set theory is one example of that. And I found like a quote from Wittgenstein that says, it says, set theory is utter nonsense, laughable, and wrong. So why did he do that? Why did he say that? So his viewpoint is logic, foundation of thinking, based again on language. And I think, so I'm not entirely sure how to interpret is what he meant by that, but one way to interpret it is actually it's completely wrong in the sense that what we mean by set inside language. So we'll have, and that's actually something interesting. We have set, we have list in computer science, we have a lot of these things, but it's not clear how related to actual language and language thinking they really are. And the question is, if we can get something closer to what we really think, then the mapping from language to that model is easier, and the language for that formal model to actual programs, something that you can execute, is also easier. And so here's an example of another example of set theory. So Ayumu, it's put short bio below here. And it's very interesting. It's an experiment by a professor in Kyoto. And you can see that basically chimpanzee, you can look at the video on YouTube, it's pretty spectacular. They would see this screen for about like 1 second, 2 seconds, and then the numbers will be blanked, and you will be able to then mark them in sequence, actually better than human. So it has some concepts of maybe sequence, but maybe it's related to sets also. So there is something which may be closer to what we actually are using. We did have a mental representation of sets before we could actually talk as a species. So I give you some other examples. So Prolog is probably a lot of people are familiar with. So programming language 74, invented by Comera and derived from first order logic. And so, which is also the same thing. It's trying to look at language and formalize a language is something which can be is entirely formal. The starting point is always language. It's always people that try to see how we think and try to formalize it. It's not happening completely ad abstracto. And you can think also at programming language. I mean, programming language, it's not clear what relation there is between the word programming language and language itself, but it's an attempt. It's also thinking and starting from language. I mean, programming language started by thinking about language. Another example, which is more maybe closer to what we have in mind when we do a semantic representation, so something like a semantic web invented by Tom Berners-Lee, like the inventor of the World Wide Web. And basically the idea is to put human knowledge in triples. So a lot of them, billions of them, like I put 2 examples here. So you have a predicate and 2 arguments, capital, France, Paris, born George Washington, 1732. And each of these things fell in its own way. So the semantic web grew to billions of entries, but then what you do with it, and then there is a lot of things that you cannot actually not represent. Prolog, my previous example, was also successful in some way, but it's also I mean, you could not mimic human reasoning really, or just some very small part of it. And you are not using that as an intermediate representation. Also, nobody is pretty much mapping what natural language processing into Prolog and then into programs these days. So there are other examples. People have really thought about what is it, how do we represent what we think. I mean, there are so some people who are really started by the language. So somebody like George Lakoff has really looked at metaphors and how they are not secondary thing, but really at the core of what we do, which is basically mapping between different representation of different objects. We use one object for another in how we compute things in our head, without actually the need of languages often. And somebody like Gilles Fauconnier, who passed away last month, I saw, had this idea of representing what he called mental spaces in which you can actually have some operations, some logical operations on representation of how we think, and trying to mimic, starting by the language, trying to really think about what we are doing. So what I'm going to do right now is just advance a little bit into my own direction and see, okay, what does it mean to think without words? And I'm going to assume, so language is everything. It's the sound, it's our ability to see things visually, to feel things, to understand gravity, to understand shock, emotions, everything. But a big part of it is vision. It's just a huge part of what we are doing. So I'm just narrowing down to vision. And my hypothesis is that if we can do it with vision, if we have vision and words together, we'll get much closer to what language actually is. And that's so the question is trying to think about what we can think without words, what this like chimpanzee Ayumu thinks. Maybe it's not so unsimilar. So I'm going to start by showing parsing visually. How can we use visual reasoning to do parsing? And so, as you know, parsing is one of the really very difficult, nearly intractable problem, and people have worked with that for a long time. And what I'm going to show you is that so I designed an algorithm that takes the ability to see certain things visually to be able to do a complete parsing of sentences. So what I'm going to say here, if you see two objects, so it's here is one-dimensional, two rectangles, like A and B here on the left, you have ways to see how they behave compared to each other, whether they are next to each other, they touch each other, they are the same, or one is smaller, one is like touches one side, is aligned with the left or less on the right. So you have this list of relationships between rectangles. So I'm going to say, okay, it's one dimension. We can do the same thing in multiple dimensions, but one dimension is actually sufficient to do parsing. And then you describe operators, comparison operators for every single one of this geometric visual relationship. So we don't really have to see what they mean. I just maybe take one here. So this point here means B is actually A is larger than B, and they are both aligned on the right side. So that's something that you can see. It's a pattern that you can recognize visually, and you have something to describe that fact. So now let me go to one example. So I take the sentence, John has been reading this book for a long time. And here I have just assuming a dictionary lookup. So dictionary lookup, you see things for each word. I have multiple possible entries, like time could be like long could be a verb, could be a noun, could be an adverb, etc. So the traditional, what's the state of parsing in general? So we have traditionally, there have been formal language parsing, things that were derived from the Chomsky hierarchy, more or less, and then the work on the compilers, programming language compilers, and trying to optimize that in many ways. So, and then the problem with that is usually, well, it's pretty much impossible to write the grammar, and then when we have the grammar, it's the complexity is exponential, and it actually never finishes, or it's the results are extremely ambiguous. Then there is another stage which is, okay, let's add some statistics there and try to do some things which is more statistical. And then the first stage at which we are more or less now is forget about parsing. We are just going to you put a huge neural network in the middle, and we are going to map it to something else. So translation, basically translation got rid of parsing. It says, okay, we can map something we don't understand into something we don't understand, but we are going to do that mapping very well. And so people are saying, yeah, but the mapping is so good that probably it understands something, but nobody has been able to say really what to really understand it, does it, and how much does it understand about syntax. So it kind of got rid of the parsing problem, and because the parsing problem is really not solved. So I've been working on that problem for a very long time. I really didn't give up from the first point, which is, well, can we do better? Can we do something which is smaller than huge neural networks? And the intuition is, if you actually look at sentences by hand, you see that there is always something which is pretty obvious, and a next step to do which is pretty obvious. The problem with that is that you don't know where this pretty obvious thing is going to appear. And so you see that I represented that with rectangles. So that's something that the chimpanzee could actually see. It's just, and the only thing which is meaningful here is how they are organized in a one-dimensional fashion. So where they are on a y-axis is not important, it's just for readability. Where are these things aligned to each other, etc. And now here what I would say, I will say, okay, if I see something like has been here, followed by something which is determiner, then I'm going to do something. I'm going to create a verb group. And so I realized that actually was the wrong rule, but that's fine. So basically, what I'm doing is recognizing a sequence, a pattern of patterns of rectangles. I'm going to modify that. So visually, I see a set of rectangles. I'm going to modify it, and my parsing is going to be that. I'm going to modify it until I cannot modify anymore, and this is going to be my parsing. And then I have a second rule. So let me give you maybe an example which is interesting here. So I say here, if I have a proper noun followed by some kind of verb group, so this rectangle with read here, rectangle inside this one, but a line on the right, which you can interpret as being the head of a verb group here. That's going to be this thing, so is going to be sure. So I have two colors, black and white for rectangles, and the black is what I'm sure about, the white is what's still ambiguous. And what I'm trying to do is propagate my knowledge here, and the exclamation mark in my rules indicate that I'm sure about what I'm doing here. So for instance, in the next iteration of my transformation, you see the black progresses. And so first, when I designed this algorithm, I was not trying to make something visual. I was just trying to explain what is the information that we need, and what is it that makes us possible at each point to say pretty much without ambiguity something about the sentence, right? And what you have is a path. The parsing is basically finding an unambiguous path which exists somewhere, but you don't know where it exists. You just have to trust that it will exist. And in practice, it does exist most of the time, not completely all the time, but quite often. There is a lot of things you can do without any ambiguity, as long as you're not doing it left to right, right? You are doing it from wherever you don't know where it is, and what you are working with is this visual object. You forget what the original sentence was. So here there are rules. So it basically moves a bit bottom up. Like it recognizes things that are more and more complex. And at some point, I have the sentence. I have part of the sentence. He has been reading this book, and then he has been reading this book for a long time. That's the transformation. I have a full analysis of a sentence. So here, I mean, it may not look like much, but what I've basically said also here, it's possible. We know we can produce sounds in sequence, right, with our mouth and tongue and breathing. The question is, do we need a universal grammar, right, which is distinct from visual thinking? And the answer apparently is no. You can rely on the thinking visual thinking than chimpanzee probably have to do something as complex as parsing. And something which has been tried for 40 years. So it's not a trivial problem to do parsing. And the way, basically, the way the natural language processing community is doing it is, it doesn't make sense. Let's forget about parsing. I don't think that's actually true. I don't think that's what we should do. I think we should do parsing. We should think about it. So there is a way to see that language parsing, which is the ability to recognize language, is possible with visual reasoning. And if you think about communication now, what you have, you have a path that you are going to have a path to find things, to find transformation, to do this parsing. You can imagine the person producing the speech as making sure that the listener will have the ability to actually find a path to parse, to disambiguate things. And as you know, there are two forces in languages. There is the push to make it short, right, because you want to be economical, and the push to make it long because you want to make it unambiguous. So there is some kind of balance between both. And the balance here can be viewed as the making sure that you still have, that the listener or your model of a listener can have the ability to disambiguate what you're saying. Okay, so this is, I saw one visual thing, which is one-dimensional overlap of rectangles. So now I'm going to introduce a second visual property of what we can do visually. And when I say what we can do visually is what we can do by seeing, but it's our way to internalize the way we see and reproduce, reimagine things that we see. So here I'm seeing shapes, right? So it's shapes here. I have a woman here, I have a policeman there, and then I have a woman policeman there, and I have just a person here. And if you think about it, it's just, if you see that person, if you see that woman policeman from a close distance, you would see a lot of features about her. It's a shape, you would see a lot of details about that shape. Further away, maybe you only see some of the features, and then further away, less and less. So it's being in focus and out of focus, and we can do these things, right? We can imagine things with less details and more details. So it's part of our capacity to think visually. And basically, here I represented by these shapes. And if you look carefully, you will see that this one has more detail than this one, and more detail than this one. They can be merged to something that's the least common denominator here. So that's one very important thing. It's basically what you do, and these things are basically they are trees on booleans. You can think of it that way. And basically, what you have with trees on boolean, you have an order. You define what is more in focus, what is less in focus. So you can define an algebra based on these things, and you don't want to stop there. You can actually put shapes together, right? So you have, if you think John gives an apple to Bill, you have a predicate, which is put in red here, and you have three arguments that are three different shapes. You have a sequence of shapes, like the order that existed for shape can be extended to sequences of shapes. And basically what you have, you can see these things, it's another shape, right? And you can see it with more or less feature, and some of the feature will disappear. You cannot do anything, but you can be more or less focused, which allows you to say, okay, John gives an apple to Bill. It's really the same thing. John gives a pear to Jean, for instance, in which just the difference is with just some shape we lose some feature. So this is one of the important problems. What is a noun, right? What is a noun? What is a verb? Well, maybe a noun. The difference between a noun and a verb is that if you trim enough. If you trim enough elements, this is going to be, they are going to look like what a noun is. So now let me give another example. So I'm representing shape in a little bit more understandable way. But it's still shapes, and a set of shapes like these blue things here, these are also shapes. There are sequences of shapes. They are all things that you can see at more or less detail. And I took here an article from a few years ago on CNN about like a woman being accused of murdering a boyfriend or committed suicide, something like that. And so here I'm representing, this is basically information that the parsing algorithm was able to extract from the text, right? So you find that the person is a student somewhere at Boston College, and then she has a boyfriend, and it happened in the past. So there is this when I say plus delta t, it's just a shape. There is nothing now. Is also all these things are just trees on Boolean. And you can see it that way only. Like the relationship, the arrows are actually not meaningful. They are here just to explain what's to improve readability. So and then you have other example. You have the fact that that person killed himself, and then there was a date mentioned in the article, which is extracted. So this. In order to implement that, you need to have identifier, basically SHA-1 for every single entity, which includes every set of shapes, which is meaningful in the text. And you have things which are a bit more complex, and which is somebody says something. And there is so this is where things like a semantic web and product breakdown is that you cannot represent alternate set of truth. And that's something that's, I mean, math is not really ready for. You want to, and that's an important work from Gilles Fauconnier, is the ability to say that you need to have alternate set of truths, and you need to be able to link them together. So this is, but here you again have to reimagine that as just the weird shape that I was showing in the middle. The only reason I'm typing these things here, it has two features. It's a human, it has a gender, feminine here, and here it's a human group. But they are just visual objects that you can modify here. And the important thing is that it's not static representation, it's the ability to zoom out and zoom in terms of scenario, right? If I say going to the restaurant, it may be just one statement, but it's also a list of, it could be viewed as a list of events. And you can see this list of events, succession of scenes as shapes also, but you can zoom in and zoom out, and you can zoom out in terms of other shapes, which are other. So this is where language and visual representation are really intertwined together, in the sense that language will be part of this zoom in, zoom out things, right? So if I'm saying going to a place and being at, it's really hard-coded. It's not only visual anymore. It happens at the level of language. So let me give an example. So let's go back to a set theory. What would be a way that we think about sets? So maybe an example is here. I'm showing to have set theory, I need to have what is a set. So that's a shape. That's another shape. That's a fact to have an element, an object. That's really anything. But then you have these three special shapes, which means all, or maybe more, or more, right? Rather than, and this is something which is very different from traditional thermodynamical set theory. But it's maybe closer to what we think about sets. So here is an example. Bill and Harry, their children is a set, and this set then has an element which is Chelsea, and it's actually the only element, right? So this is the way to express that. This is she's the only children of this couple here. And you can make some reasoning there. So let me. So now, what you want to do, I'm going slowly to the robotic example. Is, well, you can represent sorting, right? You suppose you want to interact with your Linux operating system. Sort is going to be represented as something. You want to represent it mentally or visually as a set of shapes which takes something and does something. And one way to do is, well, if you zoom in into that shape here, you zoom in somewhere into, you have a set representation, and then you have an ordered set. And now if I ask my robot, okay, give me the package with the oldest content, well, maybe you want it to be able to figure out that what the more means, and being able to call sort, basically to find inside its set of representation of sort, how they can be combined together to get the result that you want. So it's a way to think about program generation. So I know I'm getting towards the end, just a few minutes. And so this is what I just mentioned is how call, you just don't want to call only a function call. Ideally, you want to be able to generate a program based on what you say. And I think in order to do that, you need to have a representation of what you say, which goes a bit beyond what's done currently. And I think doing something which is along the lines of what I said, is not by no means final solution way to do it, but it's I think things will happen in that direction. So one way to think about it is okay. So pretty much familiar with large deep learning models. So GPT-2 like more than a year ago, 1.5 billion parameters, and then you have another one with Microsoft 17 billion, and then you have GPT-3 for like 175 billion parameters. So the question is, okay, can we do even worse for the more expensive, right? Because why it's some of these things are impressive, but in a way, the more parameters you add, the less you understand about what really you are doing, right? And what make my hypothesis is that if what we're doing is closer to the truth, we are going to bring the number of parameters representing language to a much smaller number. So my idea is something between 100,000 and 1 million parameters. If we find something that does parsing and some kind of reasoning, it doesn't mean it has to know everything that GPT-3 knows. It doesn't. I mean, that's not what language is. Language doesn't mean knowing a trillion documents. That's not what 5-year-olds do. But I want something that 5-year-olds can do that can be represented in between 100,000 and 1 million parameters. And I think you need a combination between things that are an integration between parsing and semantic representation, which is along that order of scale. And I think it's possible relying only practically on things that we can do it by reasoning visually. Even though language is more than that, if we can do, I think we can do language with only sounds and visual reasoning. Okay, so I finished just with that fun quote, Le Dao Te Ching. So the first 2 lines, 6th century BC, and it means, like, if you remember, this is the way, Tao, que Tao. So the way you can walk is not the way eternal. And this word that you can say, the word you can say, Ming ke Ming, Fei Chao Ming, is not the eternal thing. So first, it's fascinating. Tao is actually knowledge in Chinese. When you say Zhi Tao, it means I know. You don't just say I know, you say I know the way. That's, you have deep, some knowledge, and then what you have say. The language is what you can say in the dark. And what you have done about eternal language is like a formal language. So the language that you talk is not a formal language, it's more interesting action. And I'll stop right here.
Thank you very much, Dr. Roche, for sharing your research with us. It was extremely insightful, and I really hope we have more time. Thank you. And for now, we are going to move to the next talk.